Welcome everybody. My name is Matthias Wieczorek and I'm going to present our work on a fluoroscopy-guided robotic biopsy intervention system. First of all, full disclosure from our side, the first four authors work for the Interventional Systems GmbH in Austria, and they provide the robot which we used in our method. And I work for the Infusion GmbH. We provide software research kits for medical image processing and analysis, and we use this research kit in order to conduct this work. So let's hop into the topic. Fluoroscopic image guidance offers high resolution and real-time imaging, which is especially useful for high accuracy positioning tasks. For instance, biopsy interventions. In this work, we will present a robotic system where we use a custom end effector in order to establish a full transformation chain between robotic coordinate system and fluoroscopic coordinate system. And we do that by only using two fluoro shots. On the same two fluoro shots, we also plan the trajectory, and the alignment of the robot with respect to this trajectory is fully automatic based on the transformation chain. So first of all, a short overview over the robotic platform we are using. We use the so-called ISIS-1 robotic biopsy platform. It consists of a robot positioning unit and a control unit. Movement commands can be either issued with a handheld device or through a TCP/IP connection to a server application which is running on the control unit. And this is exactly what we will do in order to push movement commands directly from the software with respect to the planning to the robot. The robotic positioning unit consists of two modules which define a coordinate system such that the z-axis always points in the direction of the needle path. The lower module defines the positioning with respect to the x and y plane, and the upper module defines the angulation with respect to the x and y axis by just shearing against the lower module. Furthermore, both modules have slots such that you can interchange the end effector. And this was exactly what we used in this work, because what we needed to have in the end is a full transformation chain between robotic system and fluoroscopic images. So we needed to track the robot somehow. We decided to do that directly using the fluoro shots, and for that purpose we attached fluoroscopic markers to the end effector, 5 in total, and we used metal BBs for that. What you can see in the image as well are the two joints A and B, which are used to plug this end effector into the RPU, and the needle guide, which is designed such if you push the needle along the needle guide, you are ensured that it follows the z-axis defined by the coordinate system of the RPU. So what we now need to do is we need a full transformation chain from this coordinate system to the fluoroscopic images in order to transfer planning to movement of the robot. And what we need for that, first of all, is the geometry of the fluoroscopic images. We extract this information from the DICOM tags. Nearly all vendors write these tags, and you can extract the intrinsic parameters from the source to detector distance, source to patient distance, and the physical size of the detector. And this defines a pyramid shape defined by the detector position and the source position. And furthermore, you need the relative position of individual shots to each other with respect to a common world coordinate system. And this is given by the extrinsic parameters, and these informations can usually also be extracted from the DICOM tags. What is missing now is the position of the robot with respect to this coordinate system. And for this purpose, we use pose estimation. We detect the metal markers attached to the end effector in the fluoroscopic images using a Laplacian of Gaussian-based blob detection. From these detections, using the geometry, we triangulate possible candidates in 3D, and we register a reference points which are given in the coordinate system of the RPU using an iterative closest point algorithm to these possible candidates. So by doing so, we directly get a transformation chain from the RPU coordinate system to the coordinate system of the fluoroscopic images. Finally, what we also do is we do the planning directly on the fluoro shots. And what you can see here is that because we have that full transformation chain, we can also overlay the reachable area directly onto the fluoro shots. In green, you can see the region which is reachable by the positioning module, and the purple area is the angulation that you can achieve with the angulation module. And the path, of course, needs to be planned within those parameters. In order to evaluate the system, we now use two phantoms, a 3D printed model which holds 6 targets, and furthermore a spine model which contains 5 targets. And the spine model in addition was put into a box which was filled with wax, such that there is also haptic feedback. The targets were metal balls 2 mm diameter, such that they can be seen in a CT. So what we now did for evaluation is, for each of these targets, we planned a trajectory and executed the needle insertion. And afterwards, we took a CT with the very same C-arm we used. And this C-arm was used for evaluation. Evaluation was done manually. So we took the CT, we annotated the needle path, and measured the distance to the centroid of the marker. And in this table, you can see the results for the 3D printed phantom. We tried different view angle combinations. 0 and -90 degree corresponds to the standard AP lateral shot, but we also tried others in order to investigate the influence of that. And what you can see is that for all targets, on average, over the different viewing, and also for each viewing constellation on average over the individual targets, we achieve sub-millimeter accuracy. The results for the spine phantom look very similar, except for some outliers, but still on average we achieve sub-millimeter accuracy. So this brings me to my conclusion. In this work, we presented an automatic needle positioning based on two 2D fluoroscopic images. We used a robot and a custom end effector to establish a transformation chain from the robot to the fluoroscopic images in order to directly transfer planned trajectories into movement of the robot. And the very same images are used for planning the trajectory. The alignment of the robot, because of that transformation chain, can then be fully automatic. And within the experiments we conducted, we achieved sub-millimeter accuracy independent from the view directions on average. Last but not least, these were the references we used to conduct this work. Thank you very much for your attention.